Today we're going to finish section 2.2, Basic Differentiation Rules. And just to remind you of where we are, I'm going to go through really quickly the rules we had from last time so that we can jump back in and do the rest of our examples. We had 5 rules by definition, I guess you could say. The constant rule, derivatives of constants are 0. We had the power rule, derivative of x to the n is n x to the n minus 1, and we talked about the fact that n can be fractions, n can be decimals. There are a couple of things n can't be, but for the most part, that's not something we need to worry about. But we can, n's got a lot of flexibility. And then the constant multiplier rule. So if you have a constant, right, a number multiplied by a function, that number just comes along for the ride, and the rest of the function, you take its derivative with whatever rules you need. I mentioned this one here at the bottom sort of as an in-between step to remind you that when you have a line, the derivative is the slope. So whatever the slope is the coefficient in front of the x term, and the rest of it disappears. And then we have some indifference rules. So if you have functions that are added or subtracted, you just take their derivative of each of them individually. Everything works out sort of as we wished and hoped it might have. And then the last one were our sines and cosine rules, or trig rules, and there are just 2 of them. We have the other 4 trig rules later. But the derivative of sine is cosine, and the derivative of cosine is negative sine. So we were in the middle of doing some different ones. Sometimes we talked about the fact, like on this one, where in order to actually use any of the rules that we have, we've got to rewrite it with a little bit of algebra to be able to look like one of the forms that we can deal with. So this is one where the exponent, or the variable, was in the denominator, and so we pulled it up to the numerator using a negative power. And then this one, again, it was a rewriting step. We talked about dividing each of the pieces. I did mention last time, and then we ran out of time, that I was actually going to show you. Let me make mention really quick, because I told you that there was another way you could think about this. For some people, they think about this as bringing that x to the negative 2 up to the numerator. And you can do that. Let me show you what happens if you do. So if you bring it up to the numerator, that's fine, but it brings it up to the numerator as a factor, right? It is then multiplied by what's there, which means that, again, in order to do anything with it with the rules we have, you would have to distribute. And if you distribute, you're still going to end up right here. Okay, so if you don't decide to divide each of the individual pieces and you decide to bring it up as an x, or bring it up and make the exponent negative, you have to distribute, and then it applies to each of the individual pieces as well. So it's another way to think about it, and I meant to mention it last time and I forgot. We talked about the fact that if we have radicals, we can write them as rational exponents, like fractional exponents, and we can use our power rule as well. And then we saw this last example where I was showing you some really cool stuff on your calculator. And if you were able to make that work, I hope that that was the case. And if not, and you still have questions, remember to come ask me or the Success Center. It's not something that's absolutely like, if you don't learn it, you're never going to be able to do this. It's just a check step. So it's kind of nice to have it. It's like being able to look in the back of the book for the answer and confirm that you really got it right. So it is a really nice feature to know that your calculator can do. And we were here. So example number 7. The directions are the same as we had last time. They want us to find the slope of the graph of the function at the given point, and then use the derivative feature to, for graphing calculator, to confirm your results. This one has a little trig involved, though, so we're going to take the derivative. Okay, so if you'll remember from last time, what we did is we took the derivative, and then we evaluated it at the particular point we were given, the x value of the point we were given. And that gave us the answer to our problem, and then we confirmed it with a calculator. So that's what we're doing on this one as well. The variable this time is theta. And again, as a reminder, if the variable is theta is particularly inside of my math, or inside of, I keep saying my math lab, sorry, inside of WebAssign, you have to use the theta, okay? If you're changing it and interchanging it on a quiz or something, for me, I don't care. It's not that big a deal. But on this one, we'll keep it the same to just be consistent. Okay, so the 4, if you remember from last time, just stays along for the right. It's a constant multiplier. What's the derivative of sine theta? Right, cosine of theta. Okay, everybody good so far? Okay. This last part feels a little bit funny because it looks like I'm subtracting an angle off, and in some sense, yes, theta is an angle, and I understand that. But remember, theta is just a variable. It's like just having minus x at the end. Okay? So theta, standalone x, is a linear function. What's the derivative of theta?
0.
Close. If it were a constant, it'd be 0, but it's not a constant. It's 1, okay? So let me go back to showing you where I put it before, just to remind you. It's the one that I added here at the bottom. Okay, it's like that. Okay, anytime you have the variable with no exponent, I mean, it has an exponent of 1, but you don't see anything written there, right? The variable without any visible exponent, then it's the coefficient that's the derivative, and the coefficient of theta here would just be 1. So we end up with subtracting 1 at the end. So that's our derivative, okay? And then we're evaluating it at the indicated point, and the point they give us is 0, 0. So in particular, theta is 0. So I want 4 cosine of 0. So what is the cosine of 0? Do you remember? It's not 2. It's 1. It's either zeros and 1. So sine of 0 is 0, and then cosine of 0 is 1. And, this is one of those things that you did along the way in a unit circle, right? Do you guys remember your unit circle? I mean, I'm not asking you to tell me all the details of it. Do you know what I'm saying when I say unit circle? Yes. Yes. Okay, good. So, and I think I've mentioned this once before, but let me just reiterate. If the unit circle is not something you've done in a while, and for some of you I know that's the case, go get an online visual from Google, print it out, and then put it in your binder for right now or whatever you're using, and then reference it, okay? So when you get to a test, you can't use that or whatever, and you're going to have to remember the pieces of it. For the points of doing homeworks and such like that, it's a good reference point as a reminder, okay? So the cosine of 0 is 1. And so I have 4 times 1 minus 1, which gives me 3. All right, grab your calculator. Remind you how to do this, because we did it last time, but we did it really quickly. The button that is your best friend for this is Math 8. Okay? You hit the Math button, and it's the number 8 prompt, and it says nderiv. Right? This is where we are wanting to be. Now, in order to make this work, though, you need to put the function that you're given into the calculator. But I want to take one step before that. I want you to make sure that your calculator, just in case you haven't made sure that your calculator is actually in radian mode. Absolutely got to be in radian mode. Okay? So most of you have a button that says mode on there, and it looks something like this when you see the screen. And there's an option where it says radians or degrees. Have to be in radians. And once you put it there, you're not going to ever change it for calculus. Calculus is always done in radians, okay? Make sure you're in radians. And then go into y equals and put in the original function we began with, all right, which was 4 sine theta minus theta, but you just put in as 4 sine of x minus x. Okay, so this is what goes into y1. Like that. Okay? Everybody to there. Read.
What about if it's got the d over the d, like 3?
We're not there yet. We'll get to there. I just want you to put the y equals in for the moment. We will get to that notation. But that's, you have an operating system that has the notation that's different. Okay, so does everybody have this in y equals? Okay, good. So in your regular screen, your calculator, not in the graphing y equals menu at all, in the regular screen, I want you to choose math and hit the button that says 8. Math 8 is nderiv. Now, one version, like we talked about last time, is that it actually shows up and it says now on your screen nderiv with a parenthesis. It's not the one you have. The one that you have, it actually says this notation, d over d with a bar. And it puts this little box here. Equals, not equals, parentheses, sorry. And then it has a box and ends the parenthesis with a bar. Mine doesn't show this, so that's why I'm going back to what I did last time. And then it has say x equals and a box down here. Does it look like that? Pretty much? Okay, fantastic. Okay, so if you're in the first camp right here, and yours looks like this, what you'll do next is you need your screen now to say y1, comma, x, comma, whatever the x value is, and in this case, 0. Okay? So where do you get y1? Well, you get y1 equals by going into vars and selecting y vars, and then function, FNC, and then there's a y1. Okay, that's where y1 lives. It lives in the variables button. If you have this other version down here, here's what you put in. You'll put in an x right here because your variable's x. You'll put in y1 right here because y1 is where you've saved your functions.
Do you do the vars part as well?
Yes, exactly the same place. No matter which version of the calculator you have, you find y vars the same way. You find vars the same way. So the y1 is vars, y vars, function y1. And then again, you tell it what x value you're trying to evaluate at. And it's x equal to 0. And assuming that we've entered everything in the calculator correctly, it should give us the same answer as 3 that we found by doing it out with the calculus itself. Does anybody's not do that? Ben, you're looking a little confused. Let me see what you have. Okay, that part looks good. You need to close the parenthesis here. That'll fix it though. And then the cool thing is from here you can just hit second entry. It'll pull it back up and hit enter. There's your 3. So actually I'm glad I saw Ben's there to see though. His actually put 2 point, a whole bunch of 9s and then like a 3 something at the end. Did anybody do that too? Okay, here's what you need to understand. I know you think your calculator's like really smart, but it doesn't do calculus. Did you know that? It calculated this using a numerical estimation. It did not do it using the calculus techniques of actual calculus. You are smarter than your calculator. It's crazy. So when it does that and it says 2 point, a whole bunch of 9s and 3, 3, you have to understand that it's just a little confused. It doesn't really do it correctly. It's doing it with a numerical process that has an error involved. And so it's not always going to look exactly like what you expect. But if you look at it, you should say, that's pretty much 3, right? And you should realize that you're good to go. Okay? Any questions on the problem? Okay, so your calculator is very helpful at confirming if you are given an x value at which to confirm it, right? Like if this told me x equals 0, I can plug in the zeros and I can check it out. Calculator doesn't work if you're not told an x value equals 0 there. All right, another piece of this, sort of developing this just a little bit further, excuse me, we're going to find an equation of a tangent line. So we're actually going to find the tangent line to the graph at the given point. So we know how to find lines, right? We find lines. We did this last time where y is equal to mx plus b. I think we did it back in section 2.1 actually, so it's a couple days ago. And so the m is the derivative. That's what we keep finding with this method. And then we can find the b value. Or if you want to use y minus y1 equals m times x minus x1, right? Point slope form of a line, you can do it that way. Okay, so a couple ways. So we're going to use that to find our tangent line. And then on the graphing utility part, what we're actually going to do is we're going to graph the original function and graph the tangent line that we just created and confirm visually that, yeah, it's tangent line, right? It actually lies touching the curve like we were expecting for it to look. Make sense? Okay. So, again, we're working with what at this point we're calling basic derivative rules. So we're going to find the derivative of x to the 4th minus 3x squared plus 2. So what's the derivative of x to the 4th? 4x to the 3rd. Very good. And then what's the derivative of 3x squared? Yeah, 6x. And notice I put the subtraction sign between it, right? Okay, this whatever sign was there originally stays there unless for some reason you like pulling a negative down or something. What's the derivative of the 2 at the end? That's 0. If you want to write plus 0, by all means, but you don't have to. Okay, so far, this is the derivative for any value of x. But you don't care about every value of x. I really only care about the x value that I'm given, which is a 2. So now I can take this information and I can evaluate it at 2. So, what's 2 cubed? 8 times 4 is 32. 6 times 2 is 12. Whether you write this out or you don't, I just thought I didn't need a calculator, so I was going to do it real quick. And this gives you, like you said, 20. So your slope of this line is 20. Okay. You can either use this form of the line or this form of the line, and you're using this point and this slope. Okay, so let me just remind you, because it's been a couple days since we did it. If you like the y equal mx plus b, what you're doing is you're going to plug in the 20 for m, and then the point that you're given, 2, 6. 6 is y, 2 is x, and you solve for b. So 6 equals 40 plus b. What would b equal? 34 and negative, right? Okay. And then once I have that, I would write out the equation of the line as y equals 20x minus 34. That's not what I meant to do. I was just trying to tidy that up. It's a mess. All right. If you want to use the point slope form of a line, that's fine too. You would do y minus the y1 value, which is 6, equals 20 times x minus the x1 value, which is 2. And we would have y minus 6 equals 20x minus 40. And if I add my 6, then of course y equals, again, 20x minus 34. Okay, so either way, we get the same line. You don't have to show it twice. I'm just reminding you of two options. Okay, grab a calculator. In your calculator, in y1, you're going to put the original equation, and in y2, you're going to put the line that we just found for the tangent line. And I'm going to do the same so I can remind myself what it looks like. In terms of a window, I just chose the standard 10 by 10 window, all right? So negative 10 to 10, negative 10 to 10. And my graph looks something like a W. Does yours look like a W? Does it look like a W? So something like this. It's not perfect, but something sort of like that. And then it looks kind of like that there's this, I'm going to change my color to try to draw a line kind of over here-ish. You can hardly see it because it's off the screen very quickly. It's very steep. That makes sense because it's 20, right? A slope of 20. But it definitely looks like it's just barely touching that line at about an x equals to 2 value, right? So that's what we have going on. And we're like, yeah, that looks pretty good. Obviously, that doesn't absolutely confirm that you're correct, but it gives you some sort of sense that it's a reasonable value, right? That the tangent line, like if you graphed this thing and it looked like this, you should have cause for concern and say, okie dokie, I did something wrong. There's definitely something off. Okay, so let me see what yours looks like then. Yep. I think it was, you graphed this equation. We wanted this one. That's what's wrong. Yep. Okay, any other issues that your graph did not look quite like this? It doesn't look reasonable? Okay. Last question. Okay, so we talked about in section 2.1 that there are locations where tangent lines don't exist, where derivatives don't exist, where slopes don't exist, these kinds of descriptions, right? These kinds of issues going on. And one of the places that we talked about this was the idea of when it has a horizontal, or when it has a vertical tangent line, right? Well, there's also the possibility of having a horizontal tangent line. Okay, so you know what horizontal looks like, right? The horizon. So a horizontal tangent line actually happens. Let me draw the picture over here on the screen that it's talking about it. A horizontal tangent line will happen when there's a peak or a valley. It happens in a couple other spots too. Like, so this would be a place where if you're drawing tangent lines, you can see that they're positive on this side, right, slope, and negative slope on this side. So somewhere in between, it has to have a slope of 0. Okay, so peaks and valleys. One other possibility is if the graph levels off like this in the middle, right? It could happen. Does that make sense? Okay. In either case, what you can say about these particular lines, because they're horizontal, is that their slope is equal to 0. Everybody good with that? Okay, that's a fact from when you did algebra, right? Slopes of horizontal lines are 0. So what we're looking for on this one is it says to determine the points, if any, where the graph of the function has a horizontal tangent line. So this idea of having a horizontal tangent line is equivalent to asking where the derivative, this is called s prime, right? S of x equals 0. Where does the derivative equal 0? Okay. So we're going to take our derivative, but instead of evaluating at a particular point, we're going to look for where this particular slope is equal to 0 once we have found it. So we have 2x cubed over 3. It's really tempting to be worried about the fact that there's a 3 in the denominator. It's absolutely not a problem at all because 3 is a number. Okay? So we're going to treat the 2 over 3 like it's really 2 over 3, and it's just a constant and we don't worry about it. And what is the derivative of x cubed? 3x squared. So it's actually going to clean up pretty nicely here in a moment too. And then again, the over 2 part of this is just like having a 1/2. And then what's the derivative of x squared? 2x, right? So it will end up being a 1x there in the middle. And then I have minus 3x, so what's the derivative of negative 3x? Yep, just the 3 and the sign before it's negative, so it will stay negative. And then I have 27, and what's the derivative of 27? That's 0. Okay, everybody good so far? Okay. If you don't need to show it quite like that and you want to jump to what I'm going to give on my next step, that's totally fine. You see beautiful things happening with the powers that I brought down canceling with the denominators that are already there, don't you? So some of you probably saw that right away and you're like, why is she even bothering to write down the 2/3? So if that's you and you don't need to see the 2/3, then don't write it. That's fine. But for some of us, it can make it look a little bit confusing when we have those denominators present. So this actually ends up looking like 2x squared minus, and then again, those 2's cancel. So just like Jeff was saying up here, I have minus x. And then at the end, I've got negative 3. So this is my function. Just like on your exam, when we set this equal to 0, we're going to solve this by hand. There's not going to give you anything crazy enough that you're going to be like, oh my word, I have to have a calculator to do this. It's not the way the problems are going to work out. If they do start working out that way, it could be because it's a real world context. That would be an exception to what I just said, right? Real world stuff doesn't always work out nice and neat. Or you probably have made an error somewhere, and it's probably a good idea to go back and check what you've done before. This will factor. It factors quite nicely, but unfortunately it does have that 2 at the beginning, which makes it a little bit messier than what we normally have been doing so far. So I've got 2x, and what would we have next? An x, right. I mean, and then what would be the other piece inside the parenthesis with the 2x? What do you have? A minus sign?
Well, I did it differently. I factored it differently. I did the stair step thing.
Okay. But what did you get for your answer at the end is what I'm asking.
2x minus 3 and x plus 4.
Okay. Yeah, there's lots of ways to factor. So if that works, that's great for you. No problem. And we can check to make sure that this is the values that work, right? Because these have to give me 2x squared, which they do. And then these have to give me negative 3, which they do, right? And then in the middle, I need to make sure that I end up getting the right value with the right sign. So I have negative 3x in my inner terms, and I have positive 2x in my outer terms. Positive 2 and negative 3 is the negative 1. So these are the pieces that work out, so that's what we want. And then we're going to set each factor equal to 0. So 2x minus 3 equals 0. X plus 1 equals 0. What do I get from the first 2x minus 3 equals 0? 3 over 2. And you're right, the other one is negative 1. So everybody good with that? Okay, so a common mistake right here is to take those 2, stick them inside parentheses, and call that your ordered pair, but that would not be correct. Why not? They're both x values, right? These are 2 points. So I actually have 2 ordered pairs that I'm going to get as my answer. 3 halves, whoops, and negative 1 something. And I need to figure out what the ordered pair y value is for each of those. So I need to go up to the original equation I was given right here. And I have to actually evaluate this at 3/2, and I have to evaluate this at -1. So can I show you another cool calculator trick? Okay, so grab your calculator, put the original equation into y1. So 2x cubed over 3 minus x squared over 2 minus 3x plus 27. We've done table work before, where we go into the table and you put in the value. And table work is very nice when you get a whole number answer for your output. Sometimes you don't. Sometimes you get a decimal and you're not really sure what the corresponding fraction that goes with it. Maybe it's a repeating decimal, or maybe you can't even see within the screen that you're looking at what the decimal should be, if it repeats or not. So I want to show you another way to do that when it doesn't work out to a whole value. So if you want to go into your table and check to see if it works out to a whole value now, we could do that first. You're going to put in 3/2 and you put in -1. And on this one, mine is showing ugly values. Are yours showing ugly looking decimal point values for 3/2 and -1?
That's not like doing the tables.
Second, and then the graph button is the table button. Yeah, second graph should be your table. What'd you get?
23.625.
Yeah, 23.625. That's kind of an ugly decimal. It's not, I mean, it does terminate. It doesn't continue, but it's fairly ugly. Agreed? If you wanted to put the decimal point down because it terminates, you could. The other one is a repeating decimal, though. Did you put in -1?
I got a fraction.
Yeah, I got one.
Yours turned it into a fraction. What did you get?
173 over 6.
Okay, so some of your calculators will turn it into a fraction here. Many of them will not. Okay, so if you're in the boat where they don't give you back the fractional answer, let me say two things first. If the answer is a terminating decimal and you want to write down a terminating decimal, that's fine. If the answer is not a terminating decimal and it's repeating, it is really not okay in real mathematics to put the 3 with the repeating bar on the top of it that you learned back in middle school. That's not appropriate. So you need to turn it back into a fraction if you're going to get a repeating decimal going on. So I'd like to show you how to turn decimals back into fractions when that happens. So go into your regular screen, your calculator, regular screen. The 0.625 is fine because that's decimal, it terminates. You're trying to remember what the decimal that goes with that is, or the fraction that goes with that is.
I was 1/8, so.
Yeah, I think it's 5/8. All right, in your regular screen, you guys know how to find y1, right? Vars, y vars, function y1. So do that. Vars, y vars, function y1. So right now on your calculator it just says y1 on your regular screen, your calculator. Yes? Yes? Okay, good. Put a parenthesis. And then I want you to put one of those two x values that we tried to plug in. I don't care which one to start with. What was my first one? 3/2. So if I put y1 parenthesis 3/2 in parenthesis and hit enter, I get that 23.625, right? If you hit math, the very first thing that shows up on your math menu says arrow frac. Select it. Press enter. It turns back into calculator. Your calculator turns back into a fraction. It's 189 over 8. So in terms of a mixed number, it doesn't give you that, but it gives you the improper fraction, 189 over 8. Okay. We're going to do the same thing. Do vars, y vars, function y1. Put in the -1. Make sure you're using the negative button, not the minus button, the negative button. There's that 28.83 repeating. The 3 is what repeats. And you can do the same thing. You hit math, option number 1, frac, hit enter, and it's 173 over 6. For the most part, WebAssign, for the most part, gives you a decimal approximation if it wants you to. It'll say round to the nearest something or other. And if it doesn't say that, it expects you to give it in the actual form that's correct without any rounding. So this would be an example of where if you put in 8.3 and just stopped, right, 28.83, it would fuss at you and it would tell you your answer is wrong. So you would need to put in the decimal or the fractional form in order to get the credit to work out on that. All right, any questions about this? I mean, none of those little calculator stuff at the end, but just a reminder what we did. Horizontal tangent lines is we took a derivative, we set it equal to 0, and we solved. And we had to find the corresponding y value that went with the x value because it asked for the points where this occurred, not the x values where it occurred.